start recording. Okay, I guess it is recording now. Let me double check. All right, sorry about the disruption, but yeah, I think we're still revising and we're talking about like software-defined networking is all about disaggregation of control and data plane. And I was trying to provide a visualization that previous generation, there was a vertical integration of control and data plane on the same device. In like to just simplify, the control plane is now remote. It's logically centralized. It is somewhere else. It's not on that device, right? And these devices now can be dumb. They're just required to operate on packets, make very simple decisions. And they can be, they have to be dumb because they have to be fast, right? It's important. And we can talk a bit more about these, like trade-offs that one has to deal with when designing the ASICs or the silicon for networking and forwarding elements. But if you try to add more intelligence, then the cost of processing packets at high speed will just blow up, right? So to catch up with speed, it is important to keep them dumb. And that is the key for these switch elements, these switches or forwarding elements to be, like able to handle the type of scale that we're talking about that was required at the time back then. So now let's try to, take this intellectual journey on why software-defined networking, right? We briefly covered this question, but I'm going to dig a bit deeper into that question because, it is very important for us to understand what really motivated software-defined networking. And for that, we have to understand a bit about what was really going on in the networking back then and why the networking community was so frustrated with the state of affairs. And then, how did that lead to software-defined networking, or how exactly software-defined networking solved the problems at the time? So there is this very famous talk from Scott Shanker. Scott Shanker is, very famous faculty at UC Berkeley. I had privilege to write my first research paper with Scott Shanker, but Scott actually gave a talk, and this is way before I started my PhD as well. He gave this talk. I think it was delivered at Stanford on the future of networking and the past of protocols. I think I have added the link to this talk on the course website. I will highly recommend you to take a look at it. It is possible that maybe you won't understand each and everything that he's talking about. Maybe after this lecture, it will get easier to understand what he's talking about, but I think it's a very powerful talk because this talk kind of gave a lot of intellectual clarity to people who were dabbling with the same set of questions or similar set of challenges, but they didn't really had ways to channel that into some intellectual concepts, right? And this was phenomenal. Very passionate talk. I would highly recommend you all to take a look at that. So today's lecture is actually based on some of the key things that Scott covered in his famous talk. And I'll try to, make sure that I'm doing justice to all the intellectual pieces that he was trying to cover or, disseminate in that talk. So as you have learned in 176A, that we have this concept of layering in network, right? And layering, as we know, is, has been the key reason why internet has been so successful, right? So we have layering of applications that are built on top of reliable or maybe unreliable, talking about TCP or UDP transport, right? And that is built on a best effort global packet delivery IP layer, right? And that is built on best effort local packet delivery. So network layer is global packet delivery. The Ethernet or like this local area network or layer 2 that we call is the best effort local packet delivery, right? And then we have that is Ethernet is built on the physical transfer of bits. So you have these copper fiber, different techniques that we have or technologies that we have for transmitting or transferring these physical bits from one device to the other, right? So this has been the layering that has been key to the success of internet, right? And layering is very important. It decomposed the delivery of information or packets into fundamental components. And this second point I think is very, very important, is that it enabled independent but compatible innovation at each layer. So if I am a researcher, I'm trying to innovate something on a networking protocol, I don't have to worry about other layers, right? So this independent innovation or this decoupling of different functionalities was very, very phenomenal in making internet a big success. And as we all know, it has been an amazing success, right? So from the ARPANET, where it all started, to the time when it was around 2005, 2010, internet was already a huge, massive success. The dot-com boom and burst was already out there. There were so many, big companies based on internet, internet-based technologies were already out there. So it was an amazing success. And it was also an academic failure. And I'll talk about why it was an academic failure as we proceed. But that's problematic, right? And we will see why that has been a problem. So, like the approach for the networking with these type of layering principles was that it was more focused on building an artifact that works, but not a discipline that can be taught or that can be understood in a more principled, fundamental manner, right? So in other fields, in systems such as operating systems or databases, there has been there has been a stark difference from how those areas have evolved over time versus how networking was evolving, right? So when you try to teach, some of you might have already have taken operating systems classes or database classes, and what you focus on learning there is that you teach basic principles when we talk about operating systems. But you have taken 176A. I know some of you have learned a lot and are very excited about what you learned from 176A, but I also know that some of you were very intimidated by these bags of protocols that you had to understand and mug and learn about, right? And that is already a problem. That there is when you learned networking in 176A, there was not a very strong fundamental principle that you learned. Maybe one or two here and there, like mostly about the layering stuff, but beyond that, nothing much, right? And when we talk about these operating system databases, the management is relatively easy because of the abstraction that it offers, right? And when it comes to networking, it is notoriously difficult to manage. And given all these offerings that, fundamental principles, easy management, other systems were continuing to evolve and, support new age applications, but networking was becoming bottleneck for everybody, and there was a very, very strong need for some type of innovation to come in networking, because this realization that networking is not really a discipline and it is having all these issues was not new. This was maybe in late 90s and early 2000. People had this type of realization. People tried to come up with some solutions around that time, but the commercial motivation for solving this problem didn't exist. And I think sometimes the resonance between the need to do something and some real innovation coming in, that resonance between those two things is not always happening. But around 2005 to 2010 time period, when people started working on software-defined networking for the first time, there was a very strong resonance between this pull from the market and the technology push that was coming in. Right? So now you might be wondering that, hey, yes, bags of protocols and all those things, but why was networking really lagging behind? So networks, when they started, when you look at the ARPANET description, you look at the nature of the network, it's a very simple topology. It's a very simple, connectivity that one has to offer there. So they used to be very simple. But then, when the complexity increased, or this new control requirement that we had, that led to the great complexity, right? So what we mean by new control requirements, these new applications were coming out, and they had their unique set of requirements that, okay, I need to take this volume of traffic from location A to location B. I want these type of guarantees when I'm carrying this type of traffic from one location to the other, right? So depending on the nature of application and the capability that we have, depending on the type of devices, there were a lot of control requirements that were coming in. And what people were doing was to solve these control requirements, they were just building more and more complex protocols on top of the existing ones. And that just led to a great amount of complexity. Fortunately, networks were still running, right? So it didn't happen, or it didn't reach a point where things get so complex that nothing worked. Things used to fail a lot, things used to fail. Things fail even now. So you probably have learned something about these recent incidents when Slack was down or Facebook was down, and a lot of time the culprit are these traditional protocols that are still in use, and like those are the protocols that are really hard to change and get out of the system, and those are the ones that are still breaking. But like back then, networks reliability was definitely questionable, even though the networks were technically still running. And the reason why they were running was not because of anything like good about the network. It was more about that the community just took up the challenge that, okay, it's complex, so we'll train people who can master that complexity. And most of you are young enough to not know about these era where like companies like Cisco and Juniper, they had their own certification exams, which were basically testament of you mastering the complexity of running these networks, right? So there were these exams called CCIE and JNCIE. So these are the kind of I'm trying to recall. So Cisco networking something expert certification, and these were highly valued. If you have those certifications, that any top company will hire you. Even now, if you have those certificates, because software-defined networking has changed, but it has not replaced everything in the networking. So there is still a value to those certifications. And if you have those certifications, then getting a job at these top companies very easy. But things are changing, right? So they are not as valuable as they were 10 or 15 years ago. But 10, 15 years ago, if you were master of that complexity, you had a high demand in the job market. So the community was up to that task. They were able to master the complexity, and mastering complexity is a blessing because it made sure that these networks were running, but it is also a curse, right? Because like this was leading to this specific skill development, and which means that there was a workforce shortage scaling up. You only have a number of CCIE engineers who will be able to run these networks. Most of these companies were not able to scale up, innovate, because they can't afford to hire these type of engineers, right? So it's a blessing, but it's also a curse. And this is a very famous quote from Don Normal at UCSD, that mastering complexity is not same as extracting simplicity, right? And this might be a bit of a tongue twister type of phrase, but what networking community was doing was trying to master the complexity. And what other communities were doing were they were extracting simplicity with better abstractions and modularity, and that is not what networking was doing. So there is this fundamental issue that we had with the networking as a discipline, and things were growing up for a long time, and they were just waiting for some perfect timing of the making these bigger changes in the networking domain. So far, the takeaways are that networking focused on mastering complexity. There was little emphasis on extracting simplicity, especially from the control plane perspective. Sdn is all about focusing on extracting that simplicity. And before we talk about how Sdn is extracting simplicity, let's try to understand that how did other disciplines focused on extracting simplicity, right? So we'll take the example of how programming languages or programming evolved. When things were really raw and new, the focus was all on machine languages, right? So in machine languages, it was kind of like no abstraction. You were directly programming the hardware, and their mastering complexity was crucial. And I'm talking about late 60s, early 70s, maybe 80s. That if you want to be an expert in systems, you have to master this complexity of programming these type of hardware devices out there. Then as things evolved, then there were relatively higher languages, higher level languages like C that came up. There was operating system in place. There were a bunch of abstractions that simplified how you will program these these systems. The concept of file system, the concept of virtual memory, abstract data types, all these came out, and they just simplified how you will program these systems. And now when we talk about the modern languages like Python or Java, there is even more abstraction. Like there is these concept of object-oriented programming. There are these garbage collection concepts going on. So all those details are abstracted away. And when you're writing a program, you just have this nice abstraction, and you create objects, right? Do activities or do actions on those objects. And that has been how these areas have been extracting simplicity, right? And this has been the evolution of programming in general. And as I've been saying, like abstraction is key to extracting simplicity, right? And there is this very famous quote by Barbara Liskov. She's a professor at MIT, and this is what she said during her Turing Award lecture: that modularity based on abstraction is the things we are done, right? And look at the timing, 2009. This is kind of like around the time when networking community was trying to evolve from the conventional networking to software-defined networking. And there was a lot more maturity in the other disciplines about extracting simplicity, having better abstractions. It's not that the networking community didn't know about these things. It was really hard to make those changes, and like realizing that how exactly this problem should be approached. And I think like that's the bigger innovation that has happened. The realization that there is a problem and this problem needs to be solved was always there. But how do we solve this problem is something that was kind of like game changer in this time period. So now let's talk about abstractions in networking. There has been a concept of abstraction, like some type of abstraction networking. Layering is a good example. These layers are great abstractions. They simplify how you develop, like how you decompose or disaggregate different type of functionality. There are different layers, and but the challenge with that is that they only deal with the data plane. And this is related to some of the question, or one of the question that was discussed in the last class as well, that like how do you see software like where does software defined networking and layering fit in with each other, right? So the good answer to that question is that layering is an abstraction, and it is focusing more on the data plane. Sdn is focusing more on, like is also an abstraction, like, or it's a composition of multiple abstraction, but it is focusing more on simplifying control plane, right? So back then, networking lacked the powerful abstractions for control plane. And how do we find those abstractions? What are those right abstractions? And the network control problem is where we need these abstractions. So let's try to, like, this is an example that I discussed in the last lecture as well, that OSPF is one, which is a very common routing protocol. You go out in the market and then like that's the basic or the default protocol that one has to support. The routing protocol is specified in RFC 2328. RFCs, if you're not aware of that, these are documents written by practitioners in networking, and these are like basically documents that are uploaded for requests for comments, and then they specify the details of a specific protocol, and then like there is a organization that facilitates discussion on those, and then tries to come up with a version that everybody agrees on, right? So this protocol, how this protocol should be implemented is specified in this RFC, and it is 245 pages worth of information, right? And when we try to break that RFC down, so 101 pages focus on how do we build consistent, up-to-date map of the network, right? And only 4 pages focus on the description of Dijkstra algorithm, or how exactly it can be implemented that operates on that map, right? So this is a good, like example of the control plane problem that we had. And because there was this coupling of data plane and control plane, so all these control plane devices had to make their individual, like they have to independently make decisions, right? And they're all in distributed state. So first they had to maintain, or like have these communication protocols such that they can maintain an up-to-date map of the network, and then they can make some good decisions, right? So this local view that each of these devices had significantly complicated how these protocols will get implemented in the network, right? And like this is an example that has been heavily used to demonstrate or illustrate, like we're talking about 245 pages worth of a specification. Half of it is just about how do we contain or create these consistent up-to-date map of the network, and then just 4 pages to describe the key algorithm, the key intellectual contribution that that algorithm has, or that this protocol has, is just 4 pages worth of information. In fact, I would say it's just maybe 1 page is where you can, what you can use to describe the algorithm. So now let's talk about simplifying network control. So what are the requirements, right? So one requirement is that it should be able to operate without communication guarantees, right? So when I say communication guarantees, like when we have this integration of control and data plane, then they have to communicate with each other to maintain this consistent state of the network so that they can make appropriate decisions locally, right? So the requirement is that we should not have those massive communication guarantees that have to be provided between all these devices, right? So the abstraction that we need to simplify network control, one of this abstraction is that we should be able to simplify this distributed state, right? So when I say distributed state, each device has some state, and now all the other devices have to learn the state of other devices in the network so that they can make it their individual decisions, right? So this has to be simplified. Like, how is this distributed state managed? That has to be simplified. And then, the requirement for simplifying network control is that we need to compute configuration for each physical device, right? So, when I have a network of say 100 devices, 1,000 devices, I have to compute the final, when we think of a router, we have to think about a forward information base or a fib entry that has to be updated in that device. And we have to make those configuration decisions for all these physical devices. So if I am, if I have to make these decisions taking into consideration, which type of devices, which type of vendor it has, what type of CLIs it support, it will be a nightmare to work with, especially if I'm writing these control programs, right? So we definitely need, from abstraction perspective, we need simpler data models for network configurations, right? And third, we should be operate within given network level protocol. So, whatever the existing network protocol is, we should be able to operate within that, and we need some type of generalized forwarding model so that we can operate, or we can support all these network level protocols. So now let's talk about this distributed state abstraction, right? So here I'm talking about, requirements and three types of abstraction that we need. Like, we need to simplify distributed state. We need to simplify how we, the type of models that we are offering for making these network configuration decisions. And we need some abstraction for general forwarding, right? So let's first talk about the distributed state abstraction. What we really need is that, this abstraction should shield the control program from the vagaries of distributed state, right? So, whatever protocol you want to use to maintain this consistent state or whatever, the control program should not have to worry about it, right? How you enable that consistency, that should be decoupled from, what is exposed to the control program. The natural abstraction is that we should have some type of global network view, right? So we should have some type of annotated network graph, which is accessible to the control program through an API, right? Application interface. And control mechanism is now, or control program, control plane is just now a program that is using these APIs to access the state of the network, right? So this distributed protocol is now a graph algorithm, right? So let me make sure that we understand this effectively. When we had these, the conventional network where the control plane and data plane were the same things, then all the control plane elements that were sitting on these devices, they had to, run some distributed protocols to maintain a consistent view of the network, right? And there was all these protocols focus on how exactly the messages should be sent, what happens if there are losses in the packets and all those things, right? So how do you maintain a consistent state? All the focus was on that. Now, when we talk about a simplified abstraction that can make it easy for us to write these control programs, the abstraction that makes a lot of logical sense is that we should provide a global network view to the control program, right? So the control program, which is making all these intelligent decisions about routing and all those things, it should not really worry about how I will know about the state of the network. It should just get exposure to a graph, network graph, and then it should just operate on the network graph. How this network graph is capturing the actual physical state of the network, those are mechanisms that can be abstracted away from the control program, right? So this is an example of, like we are separating mechanisms from the abstractions, right? And with the abstraction that we are offering is this global network view. It is offered as an access API or network graph through an API. Control program just worries about accessing that graph. The mechanisms of these whatever the underlying driver or operating system is, it's going to be responsible for maintaining that consistent state. But that's not the problem for the control program, right? So this is a bit of a logical jump. So I want to make sure that you folks are able to understand that. If you have questions, let me know. This might be a good time to take a pause and get some feedback from you if this concept is clear. So is the concept of these abstractions important? Okay, so I have a question. What does simplifying the distributed state have to do with operating without communication guarantees? So I think you required communication guarantees to have that consistent view of the network, right? And because the state was all distributed and a consistent view was required, so there were these communication guarantees that the network had to provide, had to offer, such that it can provide some guarantees about the behavior of the network, right? So when I say communication guarantees, think about a protocol which says if probe packet is sent from device A to device B, but if it is lost, then there should be some mechanisms, some guarantees that ensure that this packet is eventually received by the other device, and then it will know about the state of the neighbor or the neighbors, and then it can make decisions, right? So these are the examples of communication guarantees that maintaining this distributed state or consistent distributed state require these communication guarantees. And we are trying to simplify that by taking away those distributed state requirements completely off and providing this logically centralized view of the network. Is that making sense? Okay. What else? Other questions? Okay, I'll move forward, but if you have questions, feel free to put that. Okay, could you clarify the vagaries of distributed state are? So vagaries, this is similar to what I answered before, right? So vagaries of these distributed state are that you have to, come up with these consistency protocols that make sure that all these devices have a consistent view of the network, right? And if I have to, so there are two ways in which I can offer consistent view. One is that I have a logical centralized view where all these devices are just communicating with one entity and sharing their state. And this one centralized entity is responsible for creating a consistent view of the network, right? The other option is that all these devices are indirectly communicating with each other so that each device has a consistent view of the network, right? Those are two different things with extremely different complexities, right? So typically centralized view, or if you can offer centralized abstraction, that is the best thing that you can do because it is always very simple, right? But that's not how these network operating systems were. These all network devices were they were just extremely distributed in nature, and they were all focusing on what protocols should we be supporting, how exactly these packets should be sent, what messages, what information should be exchanged between different devices, at what frequency that information should be exchanged, what happens if you don't receive acknowledgement from your neighbors, and all those things, right? So these are the vagaries of distributed state that I'm talking about that have been all abstracted away when we offer this global network view abstraction. We will proceed that how you enable this global network view, we'll get to that, but from the abstraction perspective, all we need to offer to this control program is hey, there is a graph, just work on this graph, right? Don't worry about the mechanisms of how we achieve this graph, right? Did that answer your question, Austin? Okay, all right, so let's proceed. So now the next thing is specification abstraction, right? So when I'm writing a control program, as I said earlier, that I have to provide configuration for each and every device, right? Technically, But should that be the job of the control program? When I'm writing a control program, should I really worry about, okay, what type of devices are there? Is it Arista device? Is that a Juniper device or Cisco device? And what type of CLIs or what type of commands it is offering? How exactly I should be interfacing with it? So these are kind of like, the challenges or the problems that we want to abstract away from the control program, right? As a control programmer, like you can think of that what really we want is that somebody who is not a networking expert should be able to write that control program software, right? So we have to abstract away as much detail as possible. We don't this person does not know how to configure anything for Arista or Cisco. So we have to simplify the abstraction that is offered to this this programmer, right? So control program should express desired behavior, and it should be responsible for implementing that behavior, right? I'm sorry. It should not be responsible for implementing that behavior. It should just express the desired behavior. And the natural abstraction that we can think of is that we should offer a simplified model of the network rather than exposing the entire network to this control program. Maybe we should offer a simplified version, simplified model of that network, so that there are enough information available so that it can, specify the goals, but then all the details don't need to be exposed to that program, right? So when we think about this hiding of details, you can, have a parallel with that, the concept of virtualization that we have in operating system, right? So what we're offering is a virtual view of the network and not the physical view of the network. And the control program should just focus on this virtual view, make decisions on that virtual view, and there should be some layer that should be responsible for translating that virtual, specification, the virtual network to the physical network, right? So that transformation, you can think of that layer, you can think of that some type of driver, right? Which is specific to type of devices and all those things, but the control program is agnostic to that, right? So it just operates, or it just specifies those decisions at a much higher level of abstraction. And then there are these layers, virtualization layers you can think of, that are responsible for translating them into the physical network, right? And then we have to think about the forwarding abstraction. The control plane needs flexible forwarding model, right? It needs flexibility in terms of how it can specify those decisions, and abstraction should not constrain the control program. So, we should not be saying that, a forwarding model is such where you can only make changes to destination IP and source IP, right? So that forwarding model should offer more flexibility, where we can have any combination of header fields and specify what type of action we want to take, right? And this is something which is different from how the networking was working, right? So, there was this boxing of type of protocols and type of fields that they can have access to, and that just limited the set of functionality that can be supported by the devices. They were basically hard coded into the devices, and then it became a bit of a problem of, what type of fields you can have access to, what type of changes you can make to the header of the particular packet. So in general, I think the key idea for this abstraction was that we should hide the details of the underlying hardware, and only focus, provide an abstraction that is general enough, focusing on some commonly available headers, which are completely agnostic to the specific protocol and completely agnostic to the specific vendor on which these rules have to be executed, right? I'll cover an instantiation of this forwarding abstraction, and that will make things a bit more clear. But the bottom line is that we need this flexible forwarding model that can support a wide range of control primitives in the network. Now, just to summarize what we have discussed so far, we talked about why software-defined networking was required. And the key idea was that, or the key motivation was that the networking community was going in the direction of mastering complexity, reaching a point where mastering complexity was unsustainable. And also, they learned from lessons from the other disciplines that, mastering complexity is not simplifying, extracting simplicity. So they realize that there is need to extract simplicity for the control plane. And the simplicity for us can be extracted by software-defined networking by finding the right abstractions. And we talked about these three different abstractions: the abstraction for the distributed state, the abstraction for specification, the abstraction for forwarding, that is enabling software-defined networking to extract simplicity, right? I know these are kind of like, very, like strong words, like, or maybe at times confusing words, simplicity, abstractions, and all those things. But I think if, like, when you slow things down and think about it, it does make sense, right? So software-defined networking is motivated because networking was not extracting simplicity. It was reaching a point where managing it was getting unsustainable. And then to extract simplicity, we have to come up with good abstractions. And there are these three different type of abstractions that we are going to talk about, or that are fundamental to software-defined networking. One is to simplify the distributed state. Second is to simplify how we make specification decisions. And third is the forwarding model. Okay, so now we are going to talk about realizing Sdn abstractions. But before we do that, maybe this is again a good time to take a small pause and think about what we have discussed so far, and feel free to ask me any questions you have. Were these terms very intimidating, confusing? This will be asked in the quiz, by the way. Okay. So we have a question, can we talk about a bit more about the distributed state? So like maybe I can take a detour in the next class to explain to you how, say, OSPF was implemented in the conventional sense, right? And maybe that will help us understand that what it really meant to maintain that consistent state in the network, right? But and then, like, that will help us understand the vagaries of distributed state and how having a logically centralized view of the network simplifies that. There is this question about the distributed state abstraction and specification abstraction both offer views of the network. So yes, I think, yes, they're both related to, in some sense, these are all related to the abstraction, right? So what is the abstraction that we're offering to the control program? So one abstraction is that, what is the state of the network, and what does this network look like, right? So like the centralized graph view is one abstraction, but hiding the details of that centralized you can think of that as an additional layer on top of this base layer, you can think of a network graph which is the physical network graph, and then additional layer of abstraction which further simplifies it to a virtual network. And then you write a control program for that virtual network, which then gets translated into the physical network, which then gets translated into the forwarding entries for each of those network elements. And there's this question about, are these natural abstractions the current direction of the industry, or your opinions are already implemented? Yeah, this is actually a very good question, because I think maybe I have not given you enough sense of what really is going on, and which phase are we in, right? So these are I would say not the current direction, but these are actually now you can think of them as fundamental abstractions that have been embraced by the networking community, both in academia as well as industry. So we will cover in this class the distributed state abstraction, the network operating system, how they embraced all these abstractions, how they supported all these abstractions, and how they were game changers in making forward strides when it comes to networking. So yes, these natural abstractions from presentation perspective, I'm trying to explain that, like these were the natural things that people would do, but they eventually did that. And now we have realizations of those abstractions that are, in production. So companies like Google, Microsoft, Amazon, everybody is using a variant or a realization of these abstractions. Okay, more questions? These are all good questions. So, like, please continue to asking these questions. Okay, so maybe we can move a bit forward, but if you have more questions, I'll keep an eye out on the chat. So now we're talking about, like so far we talked about the abstractions as, Garrett was getting as like, are these as natural or realization? So they were natural abstractions. Something to note is that I don't think the way I am presenting these is how things actually evolved, right? So, like what I'm trying to present to you is a bit more disciplined approach of, a bit of a top-down approach that, okay, we need to extract simplicity, we need abstractions for that. Now we understand what type of abstractions are really required. Now we're talking about how these abstractions are realized. But something to understand is that this is not how networking researchers really worked. They basically worked the other way around, right? So basically they started thinking about, okay, like what are the realizations that will solve the problem at hand right now, and then they try to put some broader perspective on, okay, I have done something, what does that really mean, and like how do different pieces that I have done so far kind of like fit together, and then eventually had this crystallization of ideas that I'm presenting right now. But this is not how things evolved, right? So as we will cover, we'll cover some instantiation or realizations of these abstractions. But you can later realize that there is no chronological synchrony between the sequence in which all these ideas were developed, right? So you can see there were different times at which different ideas came out, but then eventually everything kind of like like people were able to connect the dots and make sense that, okay, these realizations are instantiations of these abstractions, and these abstractions combined together can be defined as software-defined networking. So talking about distributed state abstraction, we briefly covered how we can enable that. So the core challenge is that we need to make distributed control program a logically centralized one, right? So the control program, as we saw for the Dijkstyle example, the control program was sitting on each of these devices, was focusing heavily on creating this consistent state of the network and then deciding how to make routing decisions. So the goal or the core challenge is that we need to make this distributed control problem a logically centralized one. How we can do that is that we need to gather information from network elements, right? And then we need to disseminate control commands to the network elements, right? So we need some type of, realization where we are polling the information for these devices so that we can create a consistent view of the network, offer that to the control program. Then whatever control program decides, we are able to disseminate those control commands back to the network elements, right? So this is what we need, or this is how we can achieve that distributed state abstraction. And in short, what I'm talking about is that we need a network operating system that is offering this interface between these network elements and the control program. So the network operating system that is enabling realization of, or that is enabling distributed state abstraction, is that it is interfacing with all these packet forwarding elements or network elements, providing a global network view to different control programs that we have. And when I say control programs, think about programs that are trying to do traffic engineering, programs that are trying to do load balancing, or simple general routing, point A to point B routing. Now let's talk about the specification abstraction, right? So abstraction here that we want to offer is that we want to offer a simplified model of the network. And in context of what we are trying to, what we learned from the operating system here is that the control program is just merely configuring the abstract model, right? So this abstraction offering a simplified model of the network, the control program is only operating on this simplified model. And like it is basically, rather than providing the exact physical configurations, it is offering an abstract configuration. And then it requires a new shared control layer, right? That is able to map this abstract configuration to the physical configuration. That is what I was kind of like, getting at earlier. We can visualize that a bit more. So the distributed state abstraction, we have network operating system. It is polling information or extracting, reading information from all these devices, offering a global network view. And then one approach is that these control programs directly operate on that global network view, right? But then, as we will cover later in this course, that why that can be a huge challenge. So we need another level of abstraction to extract further simplicity. And what that means is that we need a virtualization layer that is sitting on the top of this network operating system. And rather than providing this physical network view, it offers a virtual network view to the control program, right? So, you see this graph of 5 nodes, and physically all of these 5 nodes are connected with each other. But then maybe you want to, like treat them as 2 separate networks of their own, and, like not provide any connectivity between the two. So like, one program can focus on one half of the network, the other program can focus on the other half of the network. So this is basically network virtualization, right? So you're operating on a virtual view of the network in this case, and you're writing a control program that operates on that extremely simplified view of the network, right? So this is basically how we can realize this specification abstraction through network virtualization. I hope this kind of like, clarified some of the questions that you had about, like, I think Austin had this question about, like, this is, both are offering views, right? Yes, they're both offering views, but like you can think of this specification abstraction as a further refinement over the distributed state abstraction. It is further extracting simplicity. Now let's talk about forwarding abstraction. As I mentioned briefly before, switches have 2 types of compute tasks. So you can think of them that they need 2 types of brains, right? So one is the management CPU, which is, because it has to do complex stuff, so it has to be very smart, but, too much of computation means it has to be slow, from, packets perspective. And then you have a forwarding ASIC, or like integrated chip, application specific integrated chip. So, that has to be very, very fast. You're talking about a packet. So packet, data rates, high data rates, then they have to process packets really, really fast. So they have to be fast, they can be done, right? And I'll take a small detour here just to make sure that we understand this requirement well. Can anybody tell me that if we have, like a link which is processing, 1 billion packets per second, right? Then how much time it has to process one packet? Yeah, 1 nanosecond, right? So if the data rate that you want to support is 1 billion packets per second, then the time budget that you have to process one packet is around 1 nanosecond, right? So 1 billion is extremely tough. I don't think we still have switches that can support 1 nanosecond processing speed. Typically, when we are talking about the modern switches, we're looking at around 10 nanoseconds, or maybe sometimes less than 10 nanosecond worth of delay, right? So that is the budget. So like we are talking about 100 million packets per second that we can process. And now this is an exercise for you, and maybe this might be a question in the quiz as well, that if I'm talking about a budget of 10 nanosecond, and if on an average one packet is around 1400 bits, then what is the data rate that we're talking about in terms of gigabits per second or megabits per second? So maybe I'll frame that as a question in the quiz, but this is a food for thought for you. Okay, now getting back to this original discussion that we had. So the switches have 2 different type of brains. We need a forwarding abstraction in both. So CPU abstraction can be anything, we don't care that much, and it's not as big of a problem to get a good forwarding abstraction there. ASIC abstraction is more subtle because it is constrained by different type of budgets that you have in the hardware, right? So OpenFlow, as we were discussing in the last class, is an instantiation of that forwarding abstraction, right? So, like we will read about what OpenFlow really is, but OpenFlow is basically an instantiation of this forwarding abstraction that is required for the network hardware. right? And it takes into consideration, like the ASIC requirements, but it is not still specific to a particular vendor. All right, so let's try to understand the basics of OpenFlow. You can think of, OpenFlow protocol as a protocol that is used by the network operating system and the switches to interact with each other. And we have, when we talk about the switch, we are talking about the OpenFlow part. We have control path, we have the data path in the hardware, right? So this is kind of like what the switch is capable of. It might be a bit confusing for you that why do we have a control path here? We can have a switch which does not have any brain at all, but you need some processing compute power to handle things that the data path or the packet handling cannot do, right? So we have, say, two control programs, A and B, network operating system here. And these forwarding elements or these switches need a flow table, right? So you can think of that as the forwarding information based fib entries that you need in the hardware, right? And maybe I should ask you a question. This is based on your knowledge about 176A. So do you know what type of memory is used to input forwarding entries in the hardware, in these hardware switches? Can anybody tell me a bit about that? TCAM, yes, TCAM, exactly. So TCAM is one type of memory which is used. It is very good for these prefix matching based rules that you typically have in the networking, because of how these IP addresses have been designed. They're kind of they follow this tri-data structure, and TCAM is kind of amenable to that. So if you have forwarding entries that are more related to destination IPs, source IPs, TCAM is a good memory, good memory to use. It is very expensive, extremely expensive, right? So which means that you can't have too many of those entries in the data plane. So that's a constraint that we're talking about. That if you want a lot of control, you want to push a lot of rules, but then you have to worry about how much entries can you support in the TCAM, right? So it's something to take into consideration when we're thinking about the number of rules that we can push in the data plane. So the flow tables that we push can have rules something like, if header is equal to some P, then send it to port 4. And if header is equal to Q, then overwrite header with some R, add header S, and send it to port 5 and 6, right? So this is this is just an example of type of flow rules that you can add with OpenFlow. And if header, you don't recognize the header, then just send the packet to me, right? Like me being the network operating system. The plumbing primitives in context of OpenFlow, it is based on this match action primitive, right? So match is basically an arbitrary set of bits in the header, right? So you can match on any header or any new header, and it allows any flow granularity. And we will talk about what I mean by the flow granularity here. And the actions are, type of transformation that you will do on the packet, right? So basically, you can think of match as kind of like the read operations and actions as the write operations. And you forward to a port, you drop it, you send it to controller, overwrite the header with some mask, push or pop some header, header fields from the packet, forward at some specific bit rate, so do some type of rate control to the packets. So these are the type of actions that were primitive or supported by OpenFlow. And the match was basically all based on the flow space abstraction that we'll talk about really quick. But the key idea was that you can match on any combination of header fields, and then whatever packet satisfies that match rule, you apply the action. You specify a match and you specify action. Whatever packet satisfy that match rule, you apply that action to it. So flow space abstraction, you can use collection of bits to plumb flows. You can say I want to send, I want to focus on packets that are coming from Google on port 80. So port 80 like it's mostly HTTP traffic, right? So and Google, you can find out the set of prefixes that are owned by Google. So you can write rules. Like, of course, there is not just one prefix that Google owns, right? So there will be multiple prefixes. So that will mean that you will have to write multiple entries, flow entries, each matching on each prefix of Google, right? So I don't know if anybody knows how you will find a prefix of Google. Uh, can anybody tell me how? Like, if I give you a question, how will you, like, give me one prefix that belongs to Google? What will you do? Yeah, and this lookup is one approach. Okay, so this, I will give this as an exercise to you. Like this is not a graded exercise, so this is just for your curiosity. That in the next class, one of you should tell me what is, like, at least one prefix, IP prefix that belongs to Google, right? And then we will try to write a match rule that matches on a Google prefix, the source IP traffic coming from Google, and port 80, or maybe port 443, which is HTTPS traffic, right? So that will be an interesting traffic. And this is something that we will refer to some of the applications in future lectures. So this will be a good exercise to spend some time on thinking about how will you write that type of rule, okay? So, like the flow space or these headers can be pre-specified based on whatever protocols that we are using, right? So if we are using these standard TCP on IP on Ethernet protocols, then this is the sequence in which we should expect the bits to be in packets header. But OpenFlow is not limited to these conventional protocols. So you can define your own protocol. You can say, like, I don't want to use TCP, I want to use something else. I don't want to use IP, I want to use something else. So then you have to specify that, and you have to specify which set of bits exactly are you looking for. Are you looking for the third bit, fourth bit, fifth bit, right? So maybe I should ask you a question. Do you know how many bits we have in the Ethernet header? Is that variable? Is that fixed? Variable. And do we know how many bits we have for TCP? Again, is that variable or fixed? Yes. So see, these are all variables, so we can't really put a number out there easily. But like there is also an upper limit on how many bits can be spent on Ethernet frames. Like you have covered all this in 176.8, so I won't dig into the details here. But if you're curious, you can collect some packet traces using Wireshark and look into how many bits do we have for each of those type of header fields. Okay, so like OpenFlow 2.0 is the one which was like focusing on user-defined flow space rather than these conventional IP, TCP, Ethernet based. So when I first wrote my research paper, OpenFlow 2.0 didn't exist, so I had to work with the previous generation of these IP flow space rules, and then things changed, which provided a new set of opportunities, which I use for the other set of research papers that I wrote. So, like the bottom line being that if you were doing research, and even if you're doing research right now, there is a rapid pace at which things are changing. And, like you build some research prototypes and maybe they're relevant for the set of problems that we have right now, but then things keep changing and maybe your prototypes are not as relevant moving forward, right? So, so this is very fast-paced research area. And this goes to the argument that I was making earlier, that since this is so fast-paced, it is really, really difficult to teach this subject, right? But at the same time, it is very important for you, like we have already progressed 10 years, right? So 10 years is a good time to have some settling on concepts and fundamental principles. So that's what I'm trying to do. But bear with me, because this is a fast-paced area. Some of the things that you will learn here might not be as relevant 5 years down the line. But I think if we focus more on the fundamental principles, then they will go a long way for you. All right, let's move on. So let's try to understand. When I said flow space, right? So let's try to understand, if we have a good grasp on what flow space really means, right? So you can think of flow space, or one way of thinking about flow space is this, like, a very simple way of thinking about is like, this massive multi-dimensional bit vector, right? So, if you have a header, which is say 4,000 bits, right? In the worst possible case. So you can think of a bit vector that is 4,000 bits, right? And then there are, so many possible combinations of those header fields that are possible, given that you have, 4,000 bit vector, n number of possibilities. So those are the different header fields that can possibly exist, right? And what flow space specification is saying is like, you give me a combination of bits that you're interested in, right? So if I have like, let's try to simplify that. We just have two dimensions, the destination address and source address, right? So a point here that we have is a single flow, which has, which matches to the IP source address at the bottom here, destination address bottom here, right? So this is just one single flow. Now, like all flows that are coming from source address A, like in this plane, right? And they can have different destination addresses. So all like, this line, like not really plane in this context, but like this line is basically all flows that are coming from IP address A, right? And this is just two dimension. I was saying like, you can think of 4,000 dimension vector. So you can create different lines, you can create different dots, you can like, which will be specific flows, lines, which will be combination of two fields, and then like, different type of planes that can exist in that flow space, right? So it's a massive, like when I say multi, like, multi-massive dimension entity, and it is complex, but it also has some structural properties, right? So we know that IP addresses have, like prefixes, so they have some, like relationship with each other, the spatial relationship with each other, right? So it's not completely complex to think about this flow space abstraction, because there is some semantic meaning associated with an IP address and IP prefix, and most of the rules will be, like around that, or combination of fields, right? So as I was saying earlier, that if I specify a flow space rule, which is trying to match on traffic coming from all IPs that belong to Google's prefix and port 80, right? So that is all flows that share the same set of IP prefix and port number, right? So that will be the flow space that is defined by that rule, which matches on source IP of Google and the port 80. Is that concept clear? I'll try to, ask you some questions about flow space in the quiz. So if you have questions, this is probably a good time to ask that. Anyways, I think I can, in interest of time, I can move forward. But if you have questions, like use Slack to post any question that you have. I'll try to give you some, like simple examples in the quiz about the flow space. Like not too difficult, but something that will test a bit of your knowledge from 176A and bit of what we covered today. Right. So this is another example, right? Like, so now you can define a particular area, which is like, all IP addresses that are belonging in range of IP addresses, source IP addresses, destination IP addresses, all flows that belong to this range basically are, represented by this rectangle or square. Like, so these are all flows between two different subnets. So like starting from A, like, the question is that what does a vertical line mean starting from A? So A is a source address, right? So all flows that have source IP address as A will be represented by this line. Is that making sense? Perfect. All right, I think, this is, maybe I just jumped a few steps here. So this is just generalization, right? So you have n number of fields. If you think of it in terms of fields, maybe it is simpler to visualize. Maybe I scared you when I said 4,000 dimension vector. Maybe we can just think about it in terms of different fields. So IP address, source IP, destination IP, source port, destination port, protocol, right? So these 5 tuples are, very commonly used to specify a particular flow, right? So a particular flow is usually identified by these 5 tuples, right? So I think, like if you try to visualize it that way, maybe it's not as intimidating, but in 3 dimension, it's relatively easy to understand, right? So this cube, what is it telling us? That all flows that have field 2 between range, maybe I should have used some numbers here, right? So this range of field 2, this range of field 1, and where is field 9, right? So I guess like it's really hard to visualize in 3 dimension, but think of this as source IP, destination IP, and port, right? So think of this as like traffic, all traffic which is belonging to port 80 to maybe port 120. Port 120 means nothing semantically, but still calling it out. And then like range of prefixes which define this cube, right? So is that making sense? I can explain that a bit more. It's important concept to understand, right? So think of the field 2 as source IP, field 1 as destination IP, and field N in this case as port, right? Destination port, right? So we see that this is continuous, which means that whatever prefixes that we are using or whatever IP addresses that we are using are kind of like continuous, and so you can think of them as some subnets, because the subnet IP addresses are continuous with each other. So you can think of that as some /24, right? So there are like what you're specifying is all traffic where source IP is like some x/24, destination IP is some y/24, and the destination port is some range of ports, maybe between 80 to 100, right? So if you have all flows with these which match on these range of values, then they will belong to this cube in the flow space. I hope that was clear. But if I've confused you, feel free to get back to me. I'll try to explain that more. All right, so what are the properties of this flow space? So it has to be backward compatible. Current layers are a special case, so no endpoints. We don't want to have this type of abstraction such that we have to change the endpoints, right? Because that will be a deal breaker. It should be easily implemented in hardware. So like some amenability to how exactly this abstraction can be realized is important. But as we were discussing before, that TCAMs are actually suited for this type of match action table entries. So it really aligned well with what is feasible or what is amenable to implement in hardware. And strong isolation of flows, right? So this simple geometric construction, like based on what these like these cubes and squares that we were looking at, it is kind of like intuitive to see that how it ensures that there is strong isolation of flows. You can specify a particular match rule, it only matches on particular set of flows that satisfy certain conditions, right? So you can you cannot have two distinct rules like which cannot be separate, or which cannot separate two different portions of flow space with each other. And if having those type of isolations makes it very easy to verify these set of rules, and prove which rules can communicate and cannot communicate, right? So I can put a rule easily and say like, okay, all traffic that is coming from some spam website should be blocked, and that should be very easy for me to write such a rule in the network, right? So like isolation properties are important, but they're naturally guaranteed or provided by the flow space abstraction. Match action forwarding abstraction, I'll like in interest of time, I'll maybe cover this in the next lecture. I don't want to extend your time, but the gist of this discussion is like exactly how this match action primitive is realized in the hardware switches. And there is this concept of flow tables, where you specify the match action rules as flow table entries, and then like in one case, like it is basically helping you transform the package header as it goes out. And in case you are applying a sequence of actions, then you have to think about, or you have to abstract that as sequence of tables that are applied on the packet that is coming in. So I'll cover that in more detail in the next lecture. I'll cover this as well. I don't think I have time to cover that, but like I will encourage you, I'll post these slides. I'll encourage you to take a look at that. It will give you a sense of how these realizations have happened, but I will explicitly cover that in the next lecture, because some of you had confusions about what is theoretical versus what has been done, and what what is the current trend out there. So I'll do a comment on that in the next lecture for you folks. All right, so before I let you folks go, I just want you to have this clear takeaways from the lecture, that layering abstraction was a great innovation, right? But it only was applicable for data plane. And before software-defined networking, rose, networking focused all about, like, networking was all about mastering complexity, not a good trait for a discipline, which people eventually realized. And the key goal of software-defined networking was to come up with abstraction, which enables extracting simplicity, right? And the three abstractions that enable that were this distributed state abstraction, specification abstraction, and forwarding abstraction. And SDN realizes all these with these three, realizations: network operating system for distributed state, virtualization for specification, and OpenFlow is one of the realization for forwarding, right? So, like, in this class, we will cover all these things in great detail, like as the building blocks for software-defined networking. We'll talk about different type of network operating system. How did they realize this distributed state abstraction? We talk about OpenFlow. We'll talk about other abstractions as well, and we'll also talk about different type of further programming abstraction that were offered in terms of programming languages that were designed explicitly for the network programming. All right. So with that, I think we're done for today. And if you have questions, just feel free to reach out to me over Slack. And of course, you can come to my office hours. And like this week, we won't have the discussion section. So